Hello, so today, this is my first video. I'm excited to share it with you. Behind me, we have what we're going to begin to learn. So we're going to be learning today about three different properties of three different formulas of trigonometric ratios. Yesterday, you reviewed the sum and difference formulas for sine, cosine, and tangent. Today, we'll be reviewing the double angle power reducing, which is not something you take to your circuit breaker and try to turn the power down in your house. No, it's not that. So that we can make a square exponent, not a square exponent, just a regular plain old to the power of 1, right? And also half angle formulas, okay? So without further ado, the first thing we're going to start with today are the double angle formulas, okay? I have two of them written up here, and then I'll get to the third, okay? The first one is the sine, right? Just like the sum and difference formula, sort of three iterations of the double angle formula, okay? The first one is the sine one, right? The sine of 2 times an angle x is 2 times the sine and cosine of that angle x, okay? Pretty simple. Just take the 2, stick it on the outside, add a cosine, and you're good to go, right? You can derive that from the sum of different properties of exponents. As an example, right, if x was pi over 4, right, and we borrowed this property, or used it, so to say, we would get 2 times sine of pi over 4 times the cosine of pi over 4, right? Which are both 1 over the square root of 2, which equals 1/2 times 2 is 1, which is also equal to the sine of 2 times that measure of the angle x, pi over 4. Also the same thing as sine of pi over 2, okay? So that's the double angle property of cosine. The double angle property, sorry, of sine. I'm getting ahead of myself. The double angle property of cosines is as follows, all right? The cosine of 2 times an angle x is the cosine squared of that angle x and the sine squared of that angle x, okay? Now you'll notice it's very close to the Pythagorean formulas of trigonometric ratios, right? So by virtue of that, it is close to 1 minus 2 times the sine squared of that angle x, and also 2 times the cosine squared x minus 1, okay? Now what is the proof that it actually works? Well, we can also borrow that from the sum and difference properties of the cosine, right? So if we think about it, the cosine of 2 times an angle x is the cosine of an angle x plus another angle x, right? Just that angle x twice, right? Now if we use the sum property of cosines, we get the following. Cosine of x times cosine x minus sine x times sine x, which is cosine squared x minus sine squared x. Okay, so that's the proof of it right there. All right. The third iteration of the double angle formula is the following. The tangent formula. This is the most complex, but I'm sure you'll get the hang of it. So where did my marker go, first of all? Let me just use screen. Okay. Actually, 1 second. Okay, the third property is as follows, okay? It is this. The tangent of 2 times an angle x is 2 times the tangent of x divided by 1 minus the tangent squared of x, okay? So it's also very close to the trigonometric identity. So, what does it look like? Well, if we say, let's pick another fun angle. Let's say pi over 3, right? The tangent, if x is pi over 3, right? It would be the tangent of 2 times pi over 3. Right? If we just derive that, that would be 2 times the tangent of pi over 3 divided by 1 minus the tangent squared of pi over 3. Okay, the tangent of pi over 3 squared. Okay, which is the following. The tangent of pi over 3 is the square root of 3 divided by the square root of 3, right? 2 times the square root of 3 over 1 minus 3, which equals 2 times the square root of 3 divided by negative 2, which is the negative square root of 3. Okay? Which is the negative square root of 3. We can see that does work. Okay? Because it would be the same thing as saying the tangent of 2 pi over 3, and in the second quadrant, tangents. The tangent ratios are negative, right? Okay, so these are the double angle formulas. Here they are in all their glory. Here are their proofs. And thank you so much. We'll see you in the next video.